Hello, my name is Christoph Lehnert. Today I would like to introduce the concept of distributed ledger and smart contract-based approach for Internet of Things sensor applications. This concept was developed during my master thesis at Pforzheim University in Germany in cooperation with Mr. Thomas Greiner and Krishan Engel at the Institute of Smart Systems and Services. Before we start, I would like to give you a guideline for my presentation. At first, I will show you the challenges of using distributed ledger technology in Internet of Things sensor applications. Second, we will analyze the requirements for a smart contract-based approach. After that, I present a novel approach for smart contract-based IoT sensor applications. With that knowledge, it is possible to make a technology evaluation and a selection of the distributed ledger technology. After the selection of the DLT Ethereum, we designed a detailed concept based on Ethereum. The concept was implemented, and a case study on a smart contract-based software service for an industrial smart temperature sensor demonstrate applicability and benefits of the proposed approach. Finally, the results and the summary are discussed. The challenges of using a distributed ledger technology in IoT sensor applications are divided in the part distributed ledger technology and the Internet of Things sensor. Current approaches suggest DLT-based IoT architectures, which are static and only provide limited data precision in specific applications. Thus, they rely on custom tokens and additional technologies such as SQL databases. The IoT device is characterized by limited resources like computing power and energy consumption. In contrast, in this presentation, an adaptable, scalable, and purely DLT-based IoT architecture for secure and decentralized software services is proposed. It employs smart contract for the secure and decentralized interaction between users, software services, and IoT devices, such as smart sensors. Thereby, smart contracts are adjustable and their access is controlled by an address comparison of authorized wallets. The requirements analysis for the concept results in the following basic functions. The real-time behavior means that sensors deliver measured values within specified time limit. The data processing means that sensor data can be processed by different signal processing techniques. Sensors can be located at different places with the location independence. The event-based architecture will cause that the software services are automatically notified of data anomalies. With the horizontal scalability, can the systems expanded with additional sensors. The data storage and the availability means that the sensor data is stored decentrally and retrievable by users. To overcome the mentioned disadvantages, which I told you on slide 4, we design a novel approach for smart contract-based Internet of Things sensor applications. The system can be broken down into the parts smart sensor, smart contract as a software service, and the users, as shown here. The central component of the concept is one or more DLT-based software services. Each service is coupled with one or more smart sensors. The sensor data can then be accessed by different users, and the system also works when no user is accessing data through the software service. The smart sensor collect independently sensor data and upload them to the software service in the blockchain. Furthermore, the smart sensor works without an own token to keep the handling easy. The smart contract for the software service has a memory function, a logic function in which information is processed, and an event that is triggered under predefined conditions. The interaction between the user and the software service take place via front end, a so-called DApp, a decentralized application. New participants in form of sensors, users, or software services can easily be added. Relevant for the selection of the DLT are the criteria which were mentioned on slide 6 in the presentation. The technology evaluation and selection consist out of a rough pre-selection. For the pre-selection of the distributed ledger technology, the most known and most used representatives are considered which are smart contract capable. These are Hashgraph, Hyperledger, Ethereum, and IoT. At the same time, with this pre-selection, also different technological implementations of a distributed ledger technology like Tangle, Hashgraph, or blockchain are considered. In the final selection, the DLT are assessed with regard to scalability, usability, administrability, execution speed, and decentralization. This is done using the scale of positive means +1, neutral means 0, and negative means -1. These criteria results from the requirements mentioned on slide 6. The architecture should be scalable, which means that the DLT must be scalable as well. In addition, usability must be given so that a user can easily query sensor values. The administrability results from the fact that a concept should be easily extendable with more users or sensors. The decentralization is the main reason to create a system with a DLT, which is why this criterion is also evaluated. In summary and in total, the results show that Ethereum, as a representative of the blockchain technology, and IoT as a representative of the Tangle are the most suitable for this purpose. Ultimately, Ethereum is more suitable because it is ahead in terms of decentralization. The blockchain Ethereum is 100% decentralized, while the IoT still needs coordinators. Hyperledger is dropped because of the bad administrability if there are several participants. The choice finally fell on Ethereum. The detailed concept based on Ethereum consists out of the system architecture, which is divided into smart contract, decentralized application, and smart sensor, similar to the graph on slide 8. To send measured sensor values from the smart sensor to the blockchain, GEAS is part of the concept for this purpose. In GEAS, processes can be automated, and this program has also low hardware requirements to the smart sensor. Because GEAS is operated via commands in the terminal, this program is perfectly suited to automate recurring processes in a script. The concept development of the smart contract begins with the selection of the appropriate development environment for programming the smart contract. This happened in the IDE Remix and the language Solidity. Then the concept for the actual smart contract is designed. The code of the smart contract is kept as slim as possible so that the later execution of the contract is as cheap as possible. For this reason, only the elementary functions are part of the smart contract as backend because each command costs Ether. A decentralized application is part of the concept so that every user can check the values of the smart sensor from the software service. It is a browser-based front-end with graphical user interface. The smart contract components of the software services are as follows. The write administration, which is important for later access management. The event handling sets an event when sensor data exceeds a defined limit. The calibration is to adjust signal processing functions which are only accessible from the account of the contract manufacturer. The storage capability is necessary to receive new sensor data. The signal processing is for processing measured values. And last but not least, the output modes. They give the ability to report the last sensor data, contract name, or calibration status of signal processing function. With this structure, the various possibilities of a smart contract-based software service are shown. In this picture here, you can see the signal processing of new sensor data. The function for receiving a new measured value is the most extensive and therefore also the most expensive in its execution, since most of the calculation steps are required here. It begins with the idle mode and awaiting for new measured value. After that, it checks the received measured value for plausibility. The sensor data must not be greater or lesser than a previously defined value, which is why the function is aborted if the value is unrealistic. If the sensor data is within the plausible range, it is taken as the current last measured value. If a measured value exceeds the defined limit value, an event is entered in the blockchain that is irrevocably and permanently located there. The last step is the signal processing, where calculations are performed in the blockchain. The monitoring of measured values must be kept simple, since in principle every citizen should be able to access the measured value in the public blockchain. An interaction via GEES terminal or wallet is therefore not possible due to its complexity. For this purpose, it needs to be an intuitive to use step according to the block diagram here. It is a browser-based front-end. The dApp serves as a front-end with a graphical user interface and the smart contract here as back-end. The graphical user interface consists out of HTML and a cascading style sheet and JavaScript. The dApp is the term used to describe all the peripherals in an application that are required to communicate with the smart contract. The best suited form of a decentralized application in this case is a web page that displays all values within the smart contract and communicates with the blockchain using MetaMask in the browser. This web page can be called up by anyone to look up the measured parameters. Now the case study of industrial smart sensor systems for temperature monitoring. To prove the presented concept, a demonstrator is realized, which allows temperature monitoring and various locations with flexible, scalable sensors. A system of smart sensors in the drinking water supply is convinced as a safety-critical application area. There it is necessary and prescribed by standard that the temperature of the water does not exceed a defined amount of Celsius. By combining a smart sensor and a smart contract as shown in this figure here, it is possible for every citizen to call up the stored and calculated values. In order to test the presented concept, all points were implemented and then evaluated for their suitability. The implementation is segmented into the areas smart sensor for temperature measurement, which is connected to the drinking water supply. The smart contract as a software service to manage the sensor data, and a decentralized application with graphical user interface to read out the sensor data. The system of the smart sensor here consists out of a temperature sensor which is connected to a Raspberry Pi. The Raspberry Pi is powerful enough to operate a light node in the Ethereum network with Node.js and GEAS. The measured values for IoT need a certain accuracy. For calculations within the smart contract, like signal processing, note that Solidity does not support float numbers. Therefore, the concept includes a shift of the decimal point to increase the accuracy of integer calculations in signal processing. The calculation of a mean value can be used to smooth individual outliers depending on the filter factor FF, and is calculated according to Formula 2. If the number of possible measured values k is bigger than 100, then we must shift the decimal point for the calculation by 4 digits in Formula 1 and 3 to achieve mathematically an accuracy of at least 99%. The result is then rounded to a natural number for output in Formula 3. The DApp is successfully implemented together with the smart contract, and the communication with the smart contract is possible from the smart sensor. The examples shown illustrate the basic principle of an Ethereum network that can be built with IoT devices in combination with smart contracts. After the implementation, it was visible that the administrability is positive, because it is sufficient if a new sensor knows the contract address and the API to log into the system. The smart contract is a perfect example of transparency, as all events and interactions are logged and can be viewed by anyone who knows the address. The smart sensor stores the temperature readings and any overshots decentrally, unalterably, and transparently in the smart contract on the Ethereum blockchain. The contract is designed in such a way that only the most necessary arithmetical steps are carried out on it, in order to keep the execution as cheap as possible. The source code of the smart contract can be found under this link. Last but not least, the conclusion. This paper presents a novel smart contract-based approach for IoT sensor applications and a proof of this concept for an automated and secure sensor data exchange based on the DLT. The concept is flexible, requires no custom tokens, and the smart contract-based software service has an access control where the smart contract can be subsequently adjusted. This concept is also applicable to other IoT applications. The fundamental benefits are that the systems work completely without central regulators, own tokens, or SQL databases. Also, calculations are performed decentrally on the distributed ledger technology, despite the missing float support in Ethereum. This was my presentation. Thank you very much for your attention. Please give me feedback and enjoy the rest of your congress. Thanks a lot.